Hello everyone, myself Dr. Shivangi Surti from the Department of Computer Engineering in LDRP Institute of Technology and Research. In this presentation, I am going to explain the phases of compiler design part 1. In my previous video, I explained in brief the phases of compiler and various cousins of compiler: preprocessor, compiler, assembler and loader, linker. Out of them, compiler is again divided into two phases, that is analysis phase and synthesis phase. The analysis takes a source program as input, the synthesis phase gives target assembly program as output, and analysis phase generates intermediate code and symbol table. Further, analysis phase consists of the front end of the compiler and it is dependent on the source program, while synthesis phase generates the target program and it is also called backend of the compiler. Okay, now further, analysis phase is divided into 4 independent phases and synthesis phase is divided into 2 independent phases. Thus, as per the book Compiler Design by Aho, Sethi and Ullman, the design of compiler is divided into 6 independent phases. The first part in analysis phase is lexical analyzer, that will take source program as an input file. All the remaining phases will take output of its previous phase as input. Thus, lexical analyzer is the only phase that deals directly with the source program. Lexical analyzer, also known as linear analysis or scanning of the program, it groups a sequence of characters into tokens. It identifies all the words or lexemes in the source program. Now, lexeme means whenever we write any program using any source programming language, then individual words in the program are known as lexemes. For example, void is one lexeme, main is another lexeme, opening bracket is third lexeme, closing bracket is fourth lexeme, comma, semicolon, all the operators, all of them are independent lexemes. So, before designing of any compiler, the knowledge of input domain is required to check the validity of each and every lexeme. Okay. For variables or identifiers, we are defining a regular expression. So, lexical analysis phase is having either a list of all the valid lexemes or some predefined rules to check the validity of lexemes. In addition to that, it removes the white spaces, tabs, new lines, etc. It generates a sequence of tokens and passes it to the syntax analysis phase for further process. The lexical analysis phase is implemented as a finite automata and hence it uses the regular expressions to identify the lexemes. The most common error generated by lexical phase is invalid identifier. Apart from this, if it identifies any foreign word in the program, that is the word which is not predefined in the input domain of compiler, then also it generates an error. For example, here from the book I have taken an example, position is equals to initial plus rate into 60. So for this statement, lexical phase will generate the tokens as ID1 for position, ID2 for initial and ID3 for rate. For assignment operator and arithmetic operator, it will generate the token as operators, and for 60 the token generated is number, and hence the output of lexical phase is ID, 1. For each and every variable a unique identifier is assigned and all the identifiers are also entered in the symbol table. So here ID, 1 indicates that this variable is entered at first position in the symbol table. Then ID, 2 means initial variable and its attributes are stored in the second entry in symbol table and so on. Now wherever we use these variables, they are always referred by these unique entries. Another example, two declarative statements and one expression. So for number 1, number 2 and float f, it is generating ID1, ID2 and ID3. For remaining comma and operators, the same token is generated, while for number it generates the token number comma 5. Again, wherever we are using number 1 throughout the program, it refers first entry of symbol table where its attributes are also stored. So the limitation of lexical analysis phase is it can identify only validity of lexemes, that is individual words only. It cannot identify the validity of entire expression or statement. It is not so powerful. For example, it cannot match a parenthesis pair if it is correct or not. And hence, the next phase of compiler is syntax analyzer that takes an input from lexical phase. So syntax analysis is also called hierarchical analysis or parsing, which takes a sequence of tokens generated by lexical analyzer. It checks the syntactic correctness of expression, statement, blocks, functions or even entire program. For this purpose, regular expressions are not sufficient, so it uses the grammar rules, context-free grammar or context-sensitive grammar, and apply them on the sequence of tokens. Using this rule, the syntax analysis phase generates a parse tree from the sequence of tokens. If the generated parse tree is complete, means the construct is correct. If the parse tree is incomplete, means there is some syntax error in the expression or statement or even in a block. For this purpose, it also uses the recursive grammar rules. So if we analyze the errors, missing parenthesis, missing semicolon, missing operands, all these errors are generated by syntax analysis phase, because if we observe these errors from syntax point of view, something is missing. If I write only single operand in a binary operator, then syntax phase will generate an error. Let us go through an example. Again, same example where output generated by the lexical phase is ID1 equal to ID2 plus ID3 into 60. Now syntax phase will generate a parse tree as shown in the figure. Equal to is evaluated at the end and hence it is at the root position. Multiplication will be evaluated first and hence it is kept at the bottom side. So first it will evaluate ID3 into 60, then result of it will be added in ID2 and at the end result will be assigned to ID1. So in parse tree, the grammar rules are written in such a way that always higher precedence operators are at leaf side and lower level precedence are at root side. So this is the output of syntax analysis phase. This is known as an abstract syntax tree. If this tree is incomplete, for example, if I give the input A equal to B plus semicolon, then operator plus will have only single child node, that is ID2, only left hand side node is present, its right hand side child node is absent in this case and hence the generated tree will be incomplete, so syntax phase will give an error. Third phase of compiler is semantic analyzer. It will take a parse tree generated by syntax phase as an input. As the term suggests, if the program is syntactically correct, then semantic analysis phase will check meaning of the program. It will check correctness of the program. So semantic phase also depends on the programming language used and it checks for the semantic errors. Most common role of semantic analysis phase is that it gathers the type information for each and every variable as well as for each and every function. It uses the parse tree generated by the syntax phase. So here are few examples or few roles of semantic analysis phase. First, it checks the types of variables and performs typecasting. For that I have taken one example. In C language, if I write integer a equal to 5, b equal to 2, float f, and if I write f equal to a divided by b. So a divided by b, both of them are integer, so a divided by b will result into 2. On left hand side we have a float variable, and hence this result 2 will be converted into 2.000 implicitly. So semantic analysis phase will perform this implicit typecasting. It will check the data type on both the sides. If they are compatible with each other, then implicit typecasting is performed if required. In second example, f equal to a divided by 2.0, again one operand is float, so here we will get the value of f as 2.5. So this inbuilt typecasting is done by semantic analysis phase. In addition to that, it will check whether a specific operator is applicable on given operands or not. Each operator are having the specific operands permitted by the source language. For example, in C language we cannot add two strings using operator plus. The index in array cannot be float. We can use only integer values as an index in array. So semantic phase will perform these checks whether the operators applied are on correct operands or not. Then it will check the scope of variables and functions. If I have used some variable in my code but I have not declared it, then semantic phase will generate an error that the undefined symbol or variable is not declared. Then it will determine the definition of variables and functions. Which function, when we overload the function, then which function call is related with which function definition. That will be checked by semantic analysis phase. So if the function definition is missing, or even the function prototype is missing before function call, then semantic analysis phase will generate an error. So these are the few common checks performed by semantic analysis phase. In addition to that, it will add meaning into the code. So in the example of position equals to initial plus rate into 60, rate is assumed as a float variable, and hence integer value 60 is converted into float by semantic analysis phase. So it will add a meaning in the generated parse tree, and that will be output of semantic analysis phase. Some common errors checked by semantic analysis: if we use float array index, then we are getting the error like cannot convert integer to integer star, where even implicit typecasting is not possible. On both sides of assignment operator, the data types are different. If any variable is not declared, so it will check the scope rules also. Next phase in analysis phase is intermediate code generator, that will take a meaningful parse tree generated by semantic analyzer as an input, and it will generate intermediate code representation of that input. So intermediate code is nothing but it is a low level or machine like intermediate representation of the source program. It is not exactly machine code, but it is a compact representation of source program. The code should be generated in such a way that it should be easy to produce by the compiler, and it should be easy to translate into the target code. So intermediate code is closer to the target code as compared to the original source program. The variety of forms are there to generate the IC. Out of them, 3 address code is most popularly used. So each characteristic of 3 address code is that each instruction has maximum 3 operands and maximum 1 operator is permitted in addition to assignment operator. So in every statement of 3 address code there will be one assignment operator. In addition to that there can be one more operator, either unary or binary. If it is a binary operator, then 2 operands on right hand side as source operands. If it is a unary operator, then 1 operand on right hand side as source operand. Left hand side of assignment will be a destination operand. So compiler will first decide the order of evaluation, and then the expression is converted or the block is converted into 3 address code. Compiler also uses a temporary values to hold the computed results. For example, our previous case ID1 equal to ID2 plus ID3 into 60 and its equivalent meaningful parse tree. The 3 address code generated is shown here. Compiler will first convert 60 into float in step 1 and it stores the results in a temporary variable T1. So T1 equal to integer to real 60, then it is multiplied with ID3. Here ID3, that is rate, is a left operand and integer to real 60 is the right operand. So T2, another temporary variable, is generated, that is equal to ID3 into T1. Again a new temporary variable T3 is used that will add ID2 with the previous result T2, and finally value of T3 will be assigned in ID1, that is position. So if we observe this 3 address code, the advantage is that all the operators are arranged as per the evaluation order. So once intermediate code is generated, no need of original source program, and all the instructions are automatically arranged in the order of evaluation. First 60 is converted to real, then multiplication is applied, then addition is applied, and then the final value will be assigned to ID1, that is destination identifier. So due to these characteristics, it is easy to convert intermediate code into target program as compared to the original source program. For each and every construct, if else, while loop, switch case, for loop, declaration statement, for all these constructs 3 address code is available. It will always follow the syntax of maximum 3 operands and maximum 1 operator in addition to assignment. So this is the end of description of analysis phases of compiler. The reference book used is Compilers, Principles, Techniques and Tools by Aho, Sethi and Ullman. In my next video, part 2, I will explain the synthesis phase in detail. Thank you.